We're going to be going over the fundamental concepts of big data today, but before we actually begin, be sure to hit that subscribe button and click on that bell notification icon so you never miss out on any updates from us. So, without any further ado, let us get into the first subtopic that we have for today, which is Introduction to Big Data, right? For those of you who are completely new to the entire concept of big data, we're going to be going through this step by step. So, understanding the concept of what data means in the first place is extremely important because these days data is quite a generalized term. It actually covers a lot of things, but there are categories associated to it. So, firstly, by definition, data is the individual unit of information that is defined as figures or facts and is stored for later processing onto your computer hard drive. It could be anywhere, essentially any storage device, and it is divided into three parts. So the first is structured data. Now, for those of you who are coming from an SQL background, this sort of data you're quite familiar with. This is the data that is present in SQL tables with proper rows and proper columns, right? It's in proper queryable form, so to speak. You can query it pretty easily. There is structure to it, and it is the most organized form of data that exists. Secondly, we have semi-structured data. Now, this is a combination between completely a random order of data and some sort of a structure associated to it. So, for instance, you have files like JSON files, CSV files, and those files have a particular format associated to them. For instance, in CSV files, which is an abbreviation for comma separated values, all of the data records are separated by commas and delimited by line changes. So essentially, it mimics an SQL table with proper rows and proper columns, except it is in the form of a file, and you have just provided commas between the data records to differentiate between the column. So that is what essentially CSV is. So in a file format, it does have some structure to it. That is why that file format is called a semi-structured file format, and the data is called semi-structured data. And so is the case with JSON and XML and other semi-structured data sets as well. And finally, we have unstructured data. Now, this is completely random in nature. As you can see, the examples that we can see are JPG, PDF, MP3. So if you were to convert these data files into text files and see the contents of those text files, you will see completely random order of information. It would make absolutely no sense, right? So that is what unstructured data is. Now, unstructured data is the most challenging data because to derive some structure out of it, you need a lot of computing resources. You need to understand how the data behaves and a lot of other aspects as well. So these are the three types of data that exist. Now, big data has a definition. It has a distinction. It simply does not mean that the data is extremely large in size. There are other criterias as well, right? So there are five criterias in total, and these are called the five V's of big data. So, what are the five V's of big data? These are the five V's of big data: velocity, volume, variety, veracity, value. Let us go through them one by one. Velocity, the rate at which the data is being accumulated or generated should be really high, right? So, say for instance, you're working for an organization where data is coming in real time, say per minute or per hour, per second, in that sort. The data has a really high volume per second or a really high volume per minute. In that case, the rate of the data is really high. The rate of the accumulation of data is really high. So in that case, it satisfies the criteria of velocity. So if it's anywhere between the higher gigabytes to terabytes to petabytes in a day, then you can account for velocity in that particular aspect. And then we have volume. Volume means the most obvious thing about big data is that it's big. So anywhere you're storing big data, it should be extremely large in size, from terabytes to petabytes. That accounts for volumes. Next, we have Variety. Variety means that the data should not be coming from a single source, and the data can be of multiple file formats or data formats as well. So, for instance, if you're working for a big e-commerce organization like Amazon, so you have something like user data, you have something like sales data. So, both are two separate databases, right? But for people in the higher management, they need to see this data all collaborated together, right? So, they will combine that data and see it together. And basically, when you're combining data from multiple sources together and seeing it in a combined view, you're accounting for variety as well. So, any big data case, you need to have variety in the data as well. The data cannot simply be of a homogeneous source. And then we have veracity. Veracity means that the data should not be error free. So basically that means that the data should have some noise in it. Data should have some missing values in it. The data should have some wrong or inconsistent values in it. So that basically means that any data set that you'll pick that is based on real world values will always have inconsistencies in it, right? Say for instance, if somebody is generating a data set out of Facebook, so a lot of people on Facebook have created fake accounts as well with fake details, right? So if you were to perform a marketing survey, right, you cannot actually look at these fake accounts and decide your marketing strategy based on that. You need to be careful about that. So the data should have veracity as well, because any real world data set will have that. And finally, value. So whatever columns you're picking, whatever data you're picking should have some value to it, right? Say, for instance, you have a data set filled with complete random numbers, 100 random numbers, and you have a data set which has the academic records of students in an university, right? So you will not consider the data set which has 100 random numbers as the data set with value, because you cannot create any analytical model with it, because it is just a set of random numbers. They don't have any value in the real world sense of things. So now that we understand the initial concept of big data and the distinction between data and big data, let us go through the characteristics of big data, right? So firstly, the most natural problem that comes with big data is the problem to store it, right? So I just talked about the volume of big data, and it should be from somewhere around terabytes to petabytes. And these days, we hardly have 500 gigabytes to 1 terabyte of hard drive spaces in our laptops or in our working computers, right? At maximum, we have 2 terabytes, right? So it's quite a difficult issue to store big data on those computers, right? So that is the first problem that we have with big data. The second problem that we have is that it's really time taking to process, right? So for instance, if you have a data set with 10 records, 10 rows, it's very easy to process. It'll happen almost instantly, right? But if you have a data set with billions of records, right, which may be the case in big data, then obviously it'll take a lot of time to process that. Maybe days to months, depending on the processor speed that you have, depending on the number of cores that your processor has, depending on the number of threads that your processor can run simultaneously, right? So these are the two primary problems that we have with big data. So even if we had a 10 terabyte hard drive, right, and we were storing 1 terabyte of big data on it, right, we still need a very, very powerful processor to be able to process that 1 terabyte of information. So, with these problems arising, solutions also came up. The solution for the storage issue was Hadoop HDFS, and the solution for the processing issue was initially Hadoop MapReduce, and then in the modern times it is Apache Spark, right? So these are the technology stacks or frameworks, I should say, that solve the big data problem, right? So let us understand these frameworks and how these frameworks work and how big data clusters work, right? So firstly, let us understand what HDFS is. Now, HDFS is an abbreviation for the Hadoop Distributed File System. So it's quite similar to the file system that you have on your own computer, like you see in your Windows Explorer or your Mac File Explorer, right? Or your Linux File Explorer. You look at the file system over there. It's quite similar to that, except this file system is collaborative in nature. right? So that means this file system is not just based on one computer, it is based on the entire cluster of computers that you're connecting together in a network to create your Hadoop or big data cluster. So it might be confusing. Let us go through this step by step. So Hadoop is a Hadoop distributed file system is designed for storing very large files with streaming data access patterns running on clusters of commodity hardware. So, very large files means that the data can be gigabytes to terabytes and petabytes in size. The HDFS manages that storage flawlessly. Streaming data access, each analysis of the dataset involves a large portion of the dataset, so the time to read the whole dataset is more important than the latency in reading the first record, right? So basically, that means that even if the computers are far off, right? Even if the computers are not connected together at a very close range, right? If they're connected remotely together, right? That is not an issue as long as the internet speed is good, right? So for instance, the latency might be high between two particular computers, but once the request response starts, right, you still have a constant speed between those two computers and the jobs will run without any issue. So that is what streaming data access means. Basically, the latency is not that relevant unless you're doing something where latency matters a lot. Then we have commodity hardware. So commodity hardware was a concept that came up back when Hadoop was created. It was when hardware was really expensive, when RAM was really expensive. So what it essentially means is that instead of buying entire servers with a high RAM, high hard drive space, what you can do is you can install Hadoop on commodity hardware, which means you can install it on the computers that you have in your own office spaces, the everyday workstations, right? You can just reserve a certain section of those workstations and dedicate it to your Hadoop cluster. So instead of investing in an entire server farm for your Hadoop cluster, for your big data cluster, you can simply use the computers that you already have. So that is what commodity hardware means. So next up, let us understand the architecture of a big data cluster, right? So you have LAN wires in your office space, right? You have Wi-Fi in your office space. So what it essentially means is that whenever you are configuring Hadoop on your cluster, on your network, right? And you're telling all of these systems to find each other. When they start functioning, they will start sharing files with each other as well when required. And all of that happens seamlessly without you knowing any of it, right? So that is the advantage that you get with Hadoop. So if we were to map the previous diagram to a more refined and detailed HDFS architecture, so we can see that we've converted one of those computers into a name node. So we've basically configured one of the computers into a name node, and the remaining three we've configured as data nodes, right? And we've installed Hadoop on all of them. So what happens essentially is, say for instance, you are a client or you're somebody who's trying to access this particular cluster. So you have a file to upload. Essentially, you have a petabyte file or a terabyte file to upload, right? So you will contact the name node first. The name node will tell you which data nodes have free space, right? So once the name node tells you which data nodes have free space, you are connected to the data node that you need to be connected to, and then you start transferring your file there. But it does not end there. What happens is, say for instance, you have a 1 terabyte file, right? But it is almost a certainty that these data nodes will not have that much of free space, any single one of them. So what will you do? You will divide this file into three parts, right? Depending on the size of the file, depending on the block size that is configured into your HDFS, this file will automatically be divided into a lot of blocks, right? So for now, for example's sake, let us assume that that 1 terabyte file has been divided into three blocks, right? So the first block will represent by green, the second by this orangish color, and the third by this reddish color, right? So you've uploaded that file. And say for instance the green part gets uploaded on data node 1, the red part gets uploaded on data node 3, and the orange part gets uploaded on data node 2, right? So keep in mind that there may be a lot of other data nodes as well, but right now we are going with an example of only three data nodes, right? So what happens after that? The file has been divided into three equal parts and it has been stored in three data nodes, right? But what happens when you try to access it, right? When you're a client, when you try to read that file, you'll see that file as a one file. You wouldn't see it as three divided files, you will see it as one file. The combination of files and the division of files when we are writing it and reading it is managed entirely by the HDFS. So the next thing that is very important is data replication. So basically, in order to provide a data loss prevention feature, HDFS has come up with a feature called data replication, where you can set up a replication factor, right? So say for instance, you have set up a replication factor of 2. So what will happen? You store one block of data on data node 1. The data node 1's block, the screen block, will automatically be replicated two times on the nearest two data nodes or wherever the data nodes have available space. So one would be stored on data node 2, the other would be stored on data node 3. So in this particular case, even if data node 1 fails or something goes wrong with data node 1, you still have access to the first part of the file, right? So that is the advantage of data replication. So you can set up auto data replication. So whenever you store anything on the HDFS, it will automatically be replicated across the cluster as well, so that if any damage occurs, you still have access to the entirety of the file. Let us understand what MapReduce is. So we know how storage happens in Hadoop. Now we can understand how processing happens in Hadoop. Like there are two parts involved in any big data procedure. So first is storage, the second is processing. MapReduce is the programming model suitable for processing huge data, right? So MapReduce is unlike anything you've ever seen if you are not aware of the domain of big data. So basically, Hadoop is capable of running multiple MapReduce programs written in various languages like Java, Ruby, Python, and C++. So you have MapReduce libraries available for these particular languages, and MapReduce programs run in parallel. So they are very useful in performing large-scale data analysis using multiple machines in the cluster. So for those of you who are not still understanding what this means, it means that we just discussed earlier on in the HDFS architecture that we were dividing data and storing it across nodes in a cluster, across three data nodes. So for instance, here let us imagine these three data nodes, right? So this particular data node contains the green part, this contains the orange part, and this contains the red part, the third one, right? So what will happen next is that you'll map it. So firstly, any procedure, any data analytics procedure that you're performing, whatever is present in your code, it will execute in a map reduce format. So firstly, the data will be mapped. So it will be converted into key value pairs, and then the next step is same keys will go to one reduce operation. So for instance, if there are key values with the key being 1, all of the keys which are 1 and the values corresponding to them will go to one reduce operation, and all of the keys which are 2 will go to one reduce operation, right? And then you'll finally get your output essentially. So to sum it short, to give you the brief explanation of this, each data node is executing their part of the file on their processor itself. They are not actually collaborating until the output has been generated, right? Once the output has been generated, they all combine their output and show it together. So that is what parallel processing means. So instead of performing this entire operation on one computer, this entire terabyte of file, we have divided that 1 terabyte of file into three parts, and we are executing each part of that file on their respective node using their processor, dividing the entire time of the operation by 3. So you can understand how efficient this can make things. So depending on your cluster size, you can further reduce the time it would take to perform this operation as well. And we also discussed about Apache Spark, right? So there is one other technology that is used today because MapReduce, like we just discussed, is now sort of redundant, right? But based on the same concept, essentially, we have Apache Spark. So, for instance, let us look at the distinctions between MapReduce and Apache Spark. You have a big data set available to you right over here. Then you pass it through a MapReduce program and then you get your desired output. The problem with that, though, is that earlier on, when MapReduce was built in the early stages, where RAM was extremely expensive, we used to use hard drive space as a sort of replacement for RAM because RAM was really less. You had like 512 megabytes of RAM on one computer, and you had a terabyte of file, or say you had a 2 GB block size on your particular node, right? So it would take you 4 steps essentially to process all of that data if we were to go by it roughly. So problem with that is every time you're transferring that 512 MBs of data to your RAM, you're having some latency issues with read and write operations. So every time you transfer data from your hard drive to your RAM, it takes a bit of delay, right? And if you are dealing with extremely large amounts of data, that little bit of delay over time can add up. So when that adds up, your process of getting your output becomes slow. So we can see that there are read-write operations on the disk. So you're transferring the data into the RAM. The data is going into the CPU. It is being processed. It is being put back into the RAM and then being put back into your hard drive, right? So the time taken between for the data to transfer between to and fro between the hard drive and the RAM is adding up essentially. So you're getting your output, but with input output delays. So as random access memory or RAM or physical memory got cheaper, we came up with the technology called Apache Spark, which uses the Spark engine, right? So Spark engine is something that speeds up this entire process over 100 times compared to MapReduce, depending on the size of the data. For lower sized data sets, the difference is not that noticeable, but for higher sized data sets, you can definitely see the difference between the performance of Apache Spark and Hadoop MapReduce. So Apache Spark does this by using in-memory processing and the usage of shared variables across nodes, something that MapReduce did not do. So what does in-memory processing mean? In-memory processing means that when you transfer that data and say, for instance, now that RAM is cheap, you have like 64 gigabytes of RAM in mobile phones today. That is how cheap RAM has become. You can simply transfer the blocks of data that you have on your respective node on the data node and transfer the entirety of that in the RAM in just one go rather than 4 tries. So what that will do is you'll have the entire data available in your RAM at all times during the entirety of the execution of the job. So until you're closing down your Spark session, like until you're closing down your Spark job, you will have the entirety of the data set available in your RAM. So that basically reduces any possibility of input output delay between the CPU and the RAM and the hard drive because you're not dealing with the hard drive after the initial transfer. You're not dealing with it anymore. Once the hard drive has transferred the data to the RAM will store that data until the execution of the entirety of the program. And then once the execution has happened, the output can go back into the hard drive. So you're essentially minimizing all sorts of input-output delays. So this is what in-memory processing is, and essentially the usage of shared variables across nodes can help with a lot of logical aspects in programming as well. So let us look at the Hadoop ecosystem as well. We have looked at some technologies. We have looked at HDFS, MapReduce, and Spark. There are other technologies as well. The foundational elements obviously are the HDFS. So this is the storage system, and everything that is happening in the big data ecosystem is because of the storage system. So let us look at Flume. Flume is something that helps you integrate your HDFS with online APIs and services. For instance, data coming in from Twitter, Facebook, you can configure your Flume to ingest that data from time to time, and you'll get that data stored into your HDFS automatically. We have Scoop for people who are in the RDBMS business. They can essentially integrate HDFS with their RDBMS service by transferring data to and fro using the service we call as Scoop. And there are other services as well. We're not going to be going through all of them. For instance, we just uh, understood what MapReduce means. We also have Hive. So a Hive essentially is something that uses MapReduce to perform data warehousing and querying on the data present in the HDFS. So Hive can be used for that. You have Spark machine learning library. So right now we discussed Spark processing. So you have other options as well available with Spark. So using the same format that Spark uses, you can also create machine learning models out of Spark. For creating scripts using the MapReduce concept, you can use Pig. You have HBase, which is essentially a NoSQL database present for the HDFS data. We obviously discussed Spark. We have streaming services available which transfer the data in real time to your HDFS. So, say Kafka will stream the data coming from a particular source into your HDFS continuously. You have other services as well. You have Oozie for scheduling, and you have Yarn for resource allocation. So, Yarn essentially what it does is allocates resources. So, for instance, any job that you try to run on your Hadoop server, Yarn will look at the resources that are available. It'll queue your job up, and then eventually it'll get your job executed by allocating resources to these data nodes to execute that job. And if you're looking for a UI to manage all of this, right? For instance, if you don't want to deal with command line terminals, you also have UIs available, and one of these UIs is Apache Ambari. It has Zookeeper in it, which helps you manage and coordinate all of the services and frameworks that are running on your Hadoop cluster. So why big data? Why is this field so relevant, right? So let us take an imaginary scenario. For instance, there are two organizations. One is organization A and B, and these are organizations that are dealing in the same business. Both organizations are generating sales and customer data for each transaction and user sign up interaction. So, e-commerce businesses have login, and you can basically create your account, and you can perform transactions on those websites. And these organizations obviously have a record of that data. They're collecting that data. So, here the same case is happening as well. Organization A decides to use this data to improve their business, while organization B doesn't do anything with that data. It just lets that data remain in the database, and it just continues on with the buying selling model that it has. So, in the span of 2 years, what happens is organization A takes over the entire market share, and organization B goes out of business. So, why does that happen? Why would that happen? It would happen because, say, for instance, you have user and sales data. What you can do with that data is you can gain insights with regards to what the customer needs or and what the customer wants, right? And once you know that, you can improve your website. So firstly, you will detect like which particular aspects of the user interface the customer likes, and based on that, you can improve the overall experience that the customer has whenever they log into your website or your mobile application. Then, secondly, you can expand or focus your product range. So, based on what the customer likes on your website, as an e-commerce in business, say, for instance, the customer likes computer hardware a lot, right? So once you know that, you will understand like, okay, there are a lot of customers who like computer hardware. Let us expand that product range on our website, so more customers buy it, right? So and then you have some customers who are only interested in food items on your website, right? Then you will focus the recommendations for that customer only limited to food items, so that they are more inclined to buy products from your website. And then, based on those accurate recommendations, you can provide targeted ads. So a lot of these organizations also have ads on their businesses available on the side, like pop-ups and whatnot. So based on what you like, based on your activity on their website, they can target ads towards you, so that there is a statistically higher chance of you clicking on those ads and actually subscribing or buying the products that are being displayed in the ad. And finally, because of all this, because the customer gets what he actually likes, because the actual data analytics model or the machine learning model simply assesses and aggregates what the customer likes and shows that product to the customer, shows the exact recommendations that the customer actually needs, and gives the customer a good user interface. There is customer engagement and there is customer satisfaction. These are the two key things in the success of any business. And that results in better sales, obviously. And that could also result in the organization getting the entirety of the market share as well. So, kind of a similar story with Amazon as well, because they have such good data science and data analytics models present within their algorithms. They have succeeded and they have gotten to the apex of the e-commerce industry. Nobody even comes close. So, that is how important this is, big data as a concept in general. So gaining insights with regards to what the customer needs and wants, that is data analytics, and gaining insights with what the customer needs and wants when the data satisfies all of the five criteria that we had discussed, when the data is essentially of an enormous scale, which would be the case for Amazon or websites like Facebook, right? Then this entire process is called big data analytics. So, organizations are looking for talented individuals in this field, big organizations, because a lot of organizations are generating data in that magnitude. So, there is also a learning sort of progression that is involved with big data. For instance, you will start with data analytics, you can get into big data, right? And then you can get into data science with big data. You can get into machine learning with big data and artificial intelligence with big data. So, rather than transitioning from a normal data analytics career to a data science career where you're not accustomed to big data, when you know big data, you can essentially create more accurate, way more accurate models in data science and machine learning because your data set is extremely large. You know how to handle streaming data. Right? You can create these models way more accurately than anybody with just a normal data analytics experience. So that is the advantage that you get with big data as well. It gives you an edge in the industry. So the average salary in the United States for a big data analytics expert or a developer in the United States is about $110,000. In India, it's about 7.5 lakhs per annum. In the UK, it's a good 45,000 pounds. So keep in mind, this is the average salary, right? So if you're getting into the field, you'll obviously get a lesser salary than that. But the more experience you get, these salaries are not basically providing you with a limitation. You can gain more salary in it as well. You can expand your career, you can learn more technologies, and you can increase your salary based on the experience as well. So that brings us to the end of our session here today, guys. Hope you like the session. If you like the sessions, please be sure to like this video. And secondly, we post videos like this every day and we host webinars as well. So if you would like to ask us live doubts in these sessions from us, from our course advisors, you can sign up for our webinar, the link for which has been provided to you in the YouTube chat box. You can also contact our support team or our sales team that is available to provide you with all of our course details and your career advice all the time. You can also chat with our course advisors 24/7 by simply going on to intellipaat.com and opening the chat box and chatting with one of our course advisors. So that is about it from Intellipaat. Hope you had a wonderful time. Thank you and goodbye.